Seems like we're recording. Perfect. All right, back up to the top. Okay, so C-10, the second derivative test. We have two tests for relative minimums and relative maximums, and they are both derivative tests. For one, we use the first derivative. For the second one, for the second test, we use the second derivative. The key is to know that both tests have the same end result. You either found a relative minimum or a relative maximum. Sometimes one is just as good as the other. You could do the first derivative test, you could do the second derivative test, a problem could be solved either way and it's perfectly fine. There are a handful of situations where one test is better than the other. So let's kind of review what the first derivative test is/was, talk about those cases where we might want to use the second derivative test, and we'll talk about when the second derivative test doesn't work, because you see that in one of our, if you saw what you wrote down on the card, it is possible to get no conclusion from the second derivative test. So, you know, they both do the same things. Sometimes one might be more work, sometimes one might be less work. We'll see. Okay, so when we wanted to find relative minimums and maximums, we first wanted to find critical values. That's when f prime is 0 or f prime does not exist. F prime does not exist, but the function is defined. We then drew a sign chart around those critical values, and then we looked for sign changes from minus to plus or plus to minus, right? That is the first derivative test. Some spots where we may not be able to do that is if we have an implicit relationship. The problem with, we wouldn't be able to draw a sign chart for an implicit relationship. We'd actually have to draw like a sign coordinate plane with like 2 dimensions, and then we'd have to graph something on there. Like the sign chart only works when you only have one variable defining your derivative. But a lot of times our implicit relations have both x and y on them. So that's an example of where the first derivative test might fail you. And then another example, a good example of one of these is your values are given in a table. So you may not know enough about your function to give a sign chart. So we should see both of those questions. Okay, if we had more time, I'd probably have you guys think through these, but I kind of want to show some graphs and kind of this is the picture of the second derivative test. So in each case, we're going to draw a function, but we don't have the function. We know a couple pieces of information. We know that the f of, oh, there's a typo that I never fixed. The f of 2 is 3. I just have those backwards to represent the point that I have on each of these graphs. And 2 is a critical value, which means that when we draw the tangent line, we should have a horizontal tangent line. Sorry, it's not only a critical value, but it's a critical value where the derivative is 0. So draw a function that has each of these possibilities at x equals 2. So I need to draw a function that has a relative minimum right there. So obviously my function is coming down towards that point and then going back up. Does that fit all my criteria? Does it go through the point 2, 3? Yes. Is f prime of 2 0? Sure is. And does it have a relative minimum there? Yep. All right. Case 2, relative maximum. Shouldn't I just flip that thing upside down? Yeah, and I'll have the same thing. The key is I have to have that horizontal tangent line there, so I kind of have to draw something that looked like that. What's it going to look like if I have neither a minimum nor a maximum? Yeah, like an x to the 3rd power, and that's kind of what Jack was drawing in the air. So yeah, so case 3 is neither. So something like that, like an x to the 3rd. This is the picture that tells us all 3 basic bullet points of the second derivative test. If I have a critical value where my derivative is 0, what do I know about f double prime based on this graph? What does f double prime tell us about? It's concave up, right? It tells us about concavity. So we've got f double prime of x is greater than 0, which means that we're concave up. And then obviously with the relative maximum, f double prime is less than 0. And the graph that we drew is concave down, right? Now, notice the association between our words in these two cases. If I have a relative minimum, small, my graph is concave up, big. That's another reverse association, right? So with the second derivative, we have 3 associations we've now made. If you look at the second derivative sign and see it's positive or negative, that's a direct association, concave up, concave down, right? The other 2 are reverse associations, or backwards. I mean, it's not like a technical term. It's just kind of a way of saying it. But if we're talking about underestimate, overestimate, greater than 0 means underestimate, less than 0 means overestimate, right? So that's a reverse association. And now here with the second derivative test, if you know you have a relative minimum or a relative maximum, and you're using the second derivative to figure out which one you have, up means minimum, and concave down means maximum. So that's kind of reverse. But keep in mind, you can always sketch a picture to remind yourself, right? Draw a concave up function. Does that have a relative minimum or a maximum? A minimum, right? So if you forget, just draw yourself a picture. Draw a concave down function. Does that have a relative minimum or a relative maximum? Maximum, right? If same thing with tangent, just to jump back to that tangent line problem, same thing with tangent lines. Does that tangent line underestimate or overestimate the function? Under, right? It's not something that you necessarily, like if you forget, you have ways to remember it. And likewise, going back to the tangent line, you're going to you are underestimating here, right? Or overestimating. The graph is under, so you're overestimating. Sorry. I knew that answer and I just said the wrong thing. Cool. All right, and then last but not least, what do we have? And this isn't as guaranteed. This last one isn't guaranteed, but in the picture I drew, what do we have at x equals 2? What newer vocab word? Point of inflection, yeah. Now, you're not guaranteed, so I'm just going to put, we have f double prime equals 0. If that's a point of inflection, we went from concave down to concave up. You know, it's a very good possibility that we have a point of inflection, but we have a possible point of inflection in this case. But not necessarily. You actually could draw, the example for this is any of the just simple x to the power functions. So like, if you go higher than x cubed, x to the 3, x to the 4, x to the 5, all of these have a second derivative of 0 at x equals 0. Some of them have relative minimums. Some of them are like x cubed, where they have points of inflections. So you really don't get any information here. Okay, these would all, as long as you're above 3, by the time you had the second derivative, you would still have an x here. So at x equals 0, that second derivative would all be 0. Sometimes you have a point of inflection. Sometimes you have a relative minimum. If I put a negative in front of these, you'd have a relative maximum instead on those ones. So really, you can't make any conclusion. So the second derivative test does not work when f double prime is 0. The other thing that isn't going to work for the second derivative test either is the other type of critical value. If f prime of 2 was undefined, would there be a second derivative? No. If you can't find the first derivative, you can't find the second derivative, which means you can't use the second derivative test. Okay. So a lot of little stuff out of the way there. Let's get into the test and let's do some examples. We're actually going to start out the same. We're always going to look for critical values. Those are the only places local minimums and local maximums can be. This page is what you filled on your card, maybe with slightly different wording, but it's a reverse association. If you're at a critical value and the second derivative is positive, that means that you are concave up. Do you have a relative minimum? Or this person used local, whose notes I copied. A relative minimum or a relative maximum? Clearly a minimum, right? And vice versa. Here, when you're concave down, you have a local maximum. You can't use the test if f double prime is 0 or if it's undefined. Neither of them work. So unless you're getting strictly a positive or a negative number, that's the only time you can use the test. It can be any of those things. For your reference, here's a side-by-side comparison of the first and second derivative tests. In both cases, part one is almost the same. The second derivative test allows for undefined. That's a weird abbreviation there. I know I copied some of this and I haven't looked at these since last year. So any critical value where f prime is 0 or undefined, you can use the first derivative test. The first derivative needs to be defined. Otherwise, you won't be able to get a second derivative. We use a sign chart and we talk about sign changes. With the second derivative test, you're going to take those critical values and plug them into f double prime and hope you get positive or negative. Okay? Include both things in your justification. For example, this one's talking about a relative minimum at our x value because f prime of c is 0 and f double prime of c is greater than 0. Okay, again, just for reference, the examples, I'll show you exactly how to do it. Okay, so example 1 says, find the relative extrema of f of x equals x to the fourth minus 4x squared. Specifically, justify using the first and second derivative tests. So we are going to show both justifications here. So we'll do step 1 for both of them. F prime of x equals 4x cubed minus 8x. Correct? Okay. So we have to set that equal to 0. We'll factor out an x. Actually, no more than just an x. We'll factor out a 4x, leaving us with x squared minus 2. And what are my critical values? 0. Yep, 0 and then positive, negative square root of 2. Let's do one more factoring there. I remember this giving us a hiccup somewhere else. X minus square root of 2, x plus square root of 2. So since that 2 is not a perfect square, it still factors. It just, you put the square roots there instead of actually taking the square root. All right. So like we said, our critical values are x equals 0, x equals square root of 2, and x equals negative square root of 2. So this is both tests. I need to do that for both tests. Let's do the first derivative test here in green. For the first derivative test, I need to make a sign chart. That sign chart needs a 0, a negative root 2, and a positive root 2. And I need a sign for each of these factors. Blue, red. And since these are standard x plus x minus deals, you are negative up until you hit that number and positive afterwards. So starting with the 0, which is green, I am negative up until I hit the 0, positive after. Moving on to the positive square root of 2, which I wrote next, negative up until you hit positive square root of 2. And again, I'm following the root itself. And then last but not least, the red. I'll do the same, but I'm going to change over at the negative square root of 2. Minus, plus. Minus, plus, minus. Oh, no, sorry, I got ahead of myself. This should be a plus as well, which I don't need an eraser for. I was thinking of the overall signs alternating, but I was a step ahead. Giving us overall signs of negative, positive, negative, positive. I'm only going to write out one of the what I'll do is I'll write out the I'm going to write out the -2's, and then I'll do the 0 on the second derivative test, just so we don't have to write as much. I don't know if I'm saving time here. So I'm going to justify that -2 and +2, are they both the same type? Yeah, so we'll do the 2's together, and I'll do the 0's over on the other side. Otherwise, we're writing a book here. Okay, so we have what at -2 and +2, looking at the black signs? Minimum. Yep. Relative minimum at x equals 2, or sorry, x equals square root of 2 and x equals negative square root of 2, because f prime of x changes signs from minus to plus. Because of the sign change, we don't have to say that f prime of those values equals 0. But in the second derivative test, that actually is going to be mandatory. Take a look. Let's do orange here. So for the second derivative test, I need f double prime of x. I'm going to go back to my unfactored form and use the power rule one more time. 12x squared minus 8. And then all I have to do, I don't even need to factor that. I just need to find the f double prime of 0. It is -8. That was easy. I picked an easy one. So yeah, so that is all I need to do justification for x equals 0. So reverse association, I see a negative number, which means I'm concave down, so I have a relative maximum. F double prime of 0, or f single prime of 0 is 0. So we have to justify both of them. We have to say where we got the 0 from. And f double prime of 0 is less than 0. Because it's a reverse association. And it actually is less than 0. Both of those reasons. And then just for, without writing the justification, let's take a peek of it. If all you were doing was the second derivative test, I would also need to find f double prime of the square root of 2. And notice what's happening here. I am squaring my x value. That's all I'm doing it with it, right? So it doesn't matter if I plug in the square root of 2 or the negative square root of 2. I should get the same result. And that is 12 times 2 minus 8. So 24 minus 8, 16. And that does match what we've been saying about the second derivative test. This would be concave up, which means we'd have a relative minimum at both of those values. Okay. So they both do the same thing, right? You know, if it just says defined a relative extrema, your choice, unless something doesn't work out. Questions on that? Not too bad. Just more to remember. Here's one where it really comes into play nice. This problem's a pain in the neck with the first derivative test because you have to start making sign charts using trig. Here, we don't have to use a sign chart if we find this derivative with the second derivative test. Okay. So no matter which test we're doing, we want to find the relative extrema of this function. No matter which test we're doing, we need to find when that thing is 0 or undefined, but that is not going to be undefined. Notice the square root bar stops with the x. So that square root of 2 is just a coefficient. So f prime of x equals the derivative of the square root of 2x is, by x you mean, you dropped the wrong part. Square root of 2, right? The coefficient is all that's left over when you have something like that, linear, x to the first power. And then the derivative of cosine x is So we're going to put minus 2 sine x. Right. So we need to figure out when this thing equals 0. So the square root of 2 minus 2 sine x equals 0. Bring sine x over to the right, but write it on the left to give us 2 sine x equals the square root of 2. That's the thing that I always do that always throws at least one person off. I brought 2 sine over to the right, but then I wrote it on the left, and I just switched the sides in line. So sine x equals the square root of 2 over 2. And I stopped there because I realized this problem needs a domain restriction. So let's just restrict our domain from 0 to 2 pi. Why not? Okay. So on 0 to 2 pi, when does sine x equal the square root of 2 over 2? Start in the first quadrant. When are we going to get it in the first quadrant? Pi over 4, right? The middle line is the one where both are the same. Root 2 over 2, comma, root 2 over 2. I hate the way this board, so if it makes it a little bit bigger for a minute. If I'm right, I don't know if that'll even help me write. And that angle is pi over 4. Got it. Okay. Done worse. And sine is my x or my y? My y. So what other quadrant is going to have a positive sine value? Second quadrant, right? Yep. And what's the angle measurement? The 3 pi over 4, right? You're 1 pi over 4 here, and you're 1 pi over 4 short of a full pi here, so 3 pi over 4. Yep, the next one would be 5 pi over 4 if I was going down here, but that would be negative. And the last one would be 7 pi over 4 because you're 1 short of 2 full pi. And that's how I figured them all out when I have to do it off the top of my head. Okay, so it looks like my x values are, my critical values are pi over 4 and 3 pi over 4. So again, if we're doing the first derivative test, we've got to do a sign chart, but we're doing the second derivative test. All I have to do is find the second derivative and plug those two things in. So let's find f double prime of x in a different color just to separate our work. The derivative of the square root of 2 is 0 because it's just a constant, right? And negative 2 sine becomes, I heard a negative 2 cosine, right? Sine won't change its sign when it takes. Yep. Cool. Which is important because this is all about the sign. So we need to find the f double prime of pi over 4 and the f double prime of 3 pi over 4, which we already have the unit circle for. I guess I could probably fill in those values on my 3 pi over 4. That would be smart. I don't want to be green again. All right. So those values over here are now a negative x value, right? Because we are to the left of the origin. Yep. And still a positive y value because that's what we figured out earlier. Every number in those is a 2. It's harder. It doesn't write well when I'm writing that small. So it looks like f of pi over 4 is negative 2. Change back to orange. And that's an eraser, not a pen. Boom, boom, boom. Back to orange. Got it. Cool. Negative 2 times square root of 2 over 2. And I don't care what that is. I mean, obviously the 2's cancel, but that is less than 0. And the f of 3 pi over 4 is negative 2 times the negative square root of 2 over 2. And that thing is greater than 0. So we do have a relative min and a relative max here. Is pi over 4 a minimum or a maximum? Less than, yeah. Reverse association. If you're not finding concavity, go reverse. So less than means maximum. Relative max at x equals pi over 4 And that is because f prime of pi over 4 equals 0 and f double prime of pi over 4 is less than 0. And a similar sentence for 3 pi over 4. I've got my primes right. Weird. Boom. So there's nothing stopping you from using one test versus the other, short of instructions that say do this, or something just not working out for one of the tests. All right. I guess that wouldn't be me if I didn't look at Desmos, right? All right, so let's pop up Desmos, and it's root 2x plus 2 cosine x. Let's see what we got here. Square root 2 x on the outside plus 2 cosine x. Max at pi over 4. Min at 3 pi over 4. And nothing else between 0 and pi, right? It just climbs after that. We skip the whole second half of that interval. Oh, sorry, that's from 0 to 2 pi, right? So before 6.28, we don't get anything else. That's the other side of it.
Yeah, how did you do that?
How did I do what?
Get it to radian.
It always does show radians. It knows that it's working with trig, so it's giving you the pi over 4 instead of the decimal. It always does give radians. Yeah, whatever number you see there. Like if I put, like, let me just do something weird here. Like just change it up. Let's say it's cosine 1.2x. Let's see if that changes it. Oop, 1.2x. I don't know if it's going to give me. Yeah, so it just gave me a decimal there. It really just depends on whether it's a simple enough problem for it to do the radians. I guess I'm saying that off the top of my head. But yeah, because our argument was just in terms of x's, like this could be given. It would just be pi divided by 1.2 or pi times 1, some weird thing math with pi and 1.2. But yeah, cool. And I think Desmos always did that. All right, sweet. All right, example 3. Let's look at a table. This one should actually be relatively simple. There's nothing to do. The function f is twice differentiable with selected values of f, f prime, and f double prime in the table above. Find any relative extrema on the graph of f of x. Explain your reasoning. Same process, different feel. First thing I need to know to find relative extrema of f of x is when does f prime of x equal 0? No factoring, no derivatives needed. When does f prime of x equal 0? Yeah, 2 and 7. I scrolled off of it. Yep, 2 and 7. Boom. I think there would be one in here that, yeah, I didn't do any. We're going to get one of each. There's not going to be no conclusion from this one. We couldn't do the sign chart here. We'd be incorrect. You can't say something like, we're always positive to the left of the 2, because how do you know that the value at 1.5 isn't negative something? You know what I mean? We have no idea. We don't have enough information. First derivative test can't be used here. If you say positive to the left, negative to the right, you're making an incorrect conclusion. It's possible, but it's not guaranteed. What's that? That is true. But I guess the idea being that you might be negative in between 7 and 9. That's the goal. So you can't do a sign chart here. Let's use the second derivative test because it's easy. F double prime of 2 is equal to 4, which is greater than 0. So we have a Minimum, yep. And then f double prime of 7, that's this column, right, is -3, which is less than 0. So that's the opposite sign, so we've obviously got to be a relative maximum. Go ahead and write the rest of these sentences following the lead of what you see up above. Boom. Questions on that? So that's a little piece of information baked into this. If you just see a random question and they want relative minimums and maximums, you have to use the second derivative test. Chances are they would make it so it's designed to give you the wrong answer if you use the first derivative test, especially if it's multiple choice. Okay, example 4. Back to some implicit stuff. I imagine that a follow-up. No, it does say d. Oh, it should be, yeah, the y on top and the x on the bottom. Yep. Yes. That is backwards there. You could, yeah, you're absolutely right. And then you could just flip it to find dy dx, because dy dx and dx dy would be flips of each other. But that was definitely not my intention. You actually might be somewhat correct. But you know what the... Yeah. Yeah. Yep. Yeah. Kranek. Yep. I do. Okay. Does what? Can you come down at the end of class? 8:30. I will. Gotcha. He will. He will. Okay. All right, but Franklin guidance at the end of just to pick up a pass. Okay. Yeah. Okay. So this one's just asking us to find the second derivative. I'm surprised I don't have then asking for relative minimums and maximums. So let's do this one. This one should be, at least the first part of it should be quickly. The derivative of sine is cosine y, but since it's y, dy dx, and then that equals 1 plus dy dx. So on the left, I have cosine y minus 1 times dy dx, because I'm subtracting the dy dx and then factoring it out all in one step. And that should just equal 1. So dy dx equals 1 over cosine y minus 1. Will dy dx ever equal 0? No. And the thing about it being undefined, especially in the case of not undefined because you have a corner or something like that, but undefined because the denominator comes out to 0, that's not going to give you a relative minimum or a maximum, because you're going to have a vertical tangent line. I shouldn't say that. No, that could. I don't want to think that one too loud. Generally, they won't give you that type of question. Okay, so let's find d squared y dx squared. This feels just like a random problem thrown in. 2 ways to do this: quotient rule, or I could refer to this as cosine y minus 1 to the negative 1 power. That one? Okay. So let's make this equal to cosine y minus 1 to the negative 1 power. So chain rule says I've got to take the derivative of the inside first. Let's see how this looks. So I'm going to take the derivative of cosine y minus 1 first, and I'm going to put that out front. So the derivative of cosine y minus 1 is, missing something, dy dx, yep, times, back to orange, yep, times negative 1. Got it. Yep. All right, so we have, yep, so negative 1, this is just the power rule. Bring a negative 1 out front, raise it to the second power. So in the end, what I have here is I have negative sine y times dy dx is 1 over cosine y minus 1. Negative times negative is positive. And this is 1 over cosine y minus 1 to the negative 2. No, sorry, I was in my head, I was too early. That is still cosine y minus 1 to the negative 2, but I can write that as 1 over cosine y minus 1 squared. That part makes sense? Okay. So a version of this that I don't need unless I'm matching would be sine y over cosine y minus 1 cubed. Sine y pops up into the numerator. Cosine y minus 1 times the quantity cosine y minus 1 squared is cosine y minus 1 cubed. No, that was it's random how I just have that in there. I'm not sure why that's there. We got 5 and we got 6. Let's see how much. All right. Okay. All right.
It took me like 30 minutes to do it.
Yeah, they're big. Okay, so for example 5, I'm going to skip over letter A because I really want to see how much of this I can get done today. I think this is just an exercise in finding dy dx with a polynomial. What would I use for 3xy? Get louder. Product rule. Product rule. Right letter, wrong word. This is actually a really common way they do this on FRQs because you could get different forms of this depending on which side you bring stuff to. So a lot of times they'll actually give you the answer, which is nice because you can just, if you get it and you've done all the right stuff, you know that you're correct there. So we have this dy dx in our back pocket. Letter B says show that there is a point with x coordinate 3 at which the line tangent to the curve P is horizontal. There are 2 starting points where you can work with this one. You could start with the derivative, or you could start with the function itself. So I like to do it. I think it's easier to start with the derivative. If I have a horizontal tangent line at x equals 3, I can plug 3 in for x and figure out the y value that I need. Because if this is a horizontal tangent line, this numerator needs to be 0, right? Okay. I could also start by plugging 3 into the function, but I may have to factor something, or I may have to do more complicated math with that one. But the way that I'm going to show it, you could easily think that you're done when you're not done, and I'll show you why. Okay. All right, so let's take dy dx and set it equal to 0. That means that the numerator, 3y minus 2x equals 0. I'm going to actually change my notation there. And rather than setting dy dx equal to 0, I'm going to say dy dx when I evaluate at x equals 3 equals 0, which means that 3y minus 2 times 3, or 3y minus 6 equals 0. Santa. Oh boy.
That was Mikhail.
Mikhail. Nice.
Oh my god.
So y equals 2, right? Cool. All right. Now here's the thing. In order for this to be correct, then the point 3, 2 actually has to be on the curve, right? There's no guarantee an x of 3 and a y will 2 will make your tangent line horizontal. But if that point's not on the curve, then there's never a correct time to plug both a 3 in for x and a 2 in for y. So now we have to do step 2, verify that 3, 2 is on the curve. Do I have that right? Yeah. I want to just make sure I had the numbers in the correct order. And that's just a matter of plugging in and making sure that the curve comes out correctly. So I'm going to stop scrolling and just use a paper to help me with this one because you guys have it in front of you as well. So I'm going to go back through that original function, which is x squared plus 4y squared. So that's going to be 9 plus 4 times 4 equals 7 plus 3xy. 3 times 2. So we have 9 plus 16 is 25. And we have 7 plus 18 is 25. Alrighty. Cool. And then so what I'm going to say is, just to answer the question, P, which is our curve, has a horizontal tangent line because dy dx, now evaluated at xy, x comma y equals 3, 2, my actual point. That equals 0. A horizontal TL. Thank you. Don't write TL. And 3, 2 is on the curve. We'll look at a counterexample to this tomorrow in the bottom example. So we'll have a counterexample where we do find something that works out, but we don't actually get it. And honestly, if you picked any just random x value and plugged it in and solved, chances are that would not be on the, chances are you would actually find a point that isn't on the curve. So they had to do a little legwork to find that xy pair. Okay, and the last thing we'll do today, which gets me to a happy place with where we are in these notes, we have to find d squared y dx squared and use the second derivative test on that. So my dy dx wasn't too awful, but we do need to use the quotient rule. So d squared y dx squared. We're going to do the derivative of the first times the derivative of the second. So that is going to be 3 dy dx minus 2. That's the derivative of the numerator times the denominator. 8y minus 3x minus, and we're just going to flip those two roles. So 3y minus 2x, and then 8 dy dx minus 3. And then that's all going to be over 3y minus 2x, but squared. Okay.
That's a 3 round match.
Because it's quotient rule?
That makes it 8-1.
Oh, did I just write? Sorry. Oh, you know what? I gotcha. My bad. I visualized the wrong part of it. I wasn't looking at my paper. I was looking at my derivative. Thank you. No, it's over the second, so it should be over the denominator. Cool. All right, so now let's evaluate this at the point 2, 3. which isn't as bad as it looks, because what does dy dx give us? If we have a horizontal tangent line there, what's dy dx? 0. Yeah, every one of those dy dx's is a 0. So whenever you're doing the second derivative test on an implicit function or an implicit relationship, you should always be plugging 0 in for dy dx. So I end up with a big long fraction, which is 3 times 0, canceled, minus 2. I need to use I don't have my notation there. Okay. So we've got negative 2 times the quantity, 8 times 2. So I'll do this math in line. That's going to be 16 minus 9 minus, question? 8y, 16 minus 3x, 9. Yep. Minus 3y minus 2x. So that's going to be 6 minus 6. Heyo. That's awesome because that is 0. And that's going to zero out everything else, which is 8 times 0 minus 3. But who cares? Because it's 0. Good thing I didn't have that down here. And this is a repeat, 16 minus 9 squared. Yep. Yeah, so we have, negative 16 minus 9 is 7. So we've got negative 14 minus 0 over something squared, which is going to be positive. All I need is the sign. So that's going to be 7 squared, which is greater or less than 0. Yep. You don't have to fully evaluate that. If you have something that you can tell what its sign is, put your less than sign. And we have a relative maximum. And that is because dy dx evaluated at x comma y equals 3 comma 2 equals 0. And a lot of the same characters over a second time, but with squareds, evaluated at x comma y equals 3 comma 2 is less than 0. So yeah, if you're plugging into d squared y dx squared because you're at a critical value, 100% of the time, you've got to be differentiable. So you're not at a critical value because you're undefined. So 100% of the time, your dy dx is just going to be 0, which should simplify some things. All right. Other than example 6, which is a little bit more of the same, when we do it tomorrow, we'll do the, oh yeah, it is known that, so we don't need to find dy dx in that one. That should take us 5-10 minutes tomorrow to get that one done, giving you guys some time to work. Yes, you can go now. Yeah, when lecture was over, it was good. All right, so we are officially done with 3 units worth of AP Calc, and we have 4 to go.